Okay, so picking back up in lesson 2-3 on example 2. We talked briefly at the end of your class about the fact that we were going to be graphing these today. We talked about, it said to locate extrema, and you guys reminded me that extrema are mins and maxes. And when we talk about zeros, we're talking about x-intercepts. Okay, so we talked about those things. And then we're going to explain how it's related to the monomials from which it's built. So as we look at A, we're going to talk about, okay, how is this graph related to x cubed and x? So the graphs of like y equals x cubed and y equals x. So let's look at the graph to start with. Whether we look at the graph by hand or whether we graph it on the calculator, we could look at either or here. I guess it's probably something we should still kind of talk about on the calculator. And I don't think I got too big and crazy here. So, what did you guys find out about this graph? Did you graph it on the calculator? What's it look like? This was x to the third plus x, right? What's that look like to you? A lot like what? It looks a lot like x cubed, doesn't it? And in fact, one of the things I'm going to do here in a moment is we're going to graph x cubed on the same thing, but it looks a lot like x cubed. It goes through 0, 0. The difference is it doesn't go through 1, 1, does it? When we put in 1, 1 cubed is 1 plus 1, so it goes through 1, 2, and negative 1, negative 2, instead of 1, 1, and negative 1, negative 1. Okay, so it looks a lot like y equals x cubed. Okay, so we'll come back and talk about that here in a moment. Extrema. What do you see in the way of extrema? What? Yeah. It passes through 1, 2. Is that what? Yeah. And I didn't go to the calculator on that one. I just plugged the value in. So it would not plus. And actually, just glancing at the graph, it looks like it passes through 1, 1, but it doesn't. It passes through 1, 2. I think it's suddenly quiet. I hate that. Okay, just because all of a sudden I'm like, oh, adjust my voice level for the moment. Sorry. I'll try not to yell at you. Okay. Extrema? Do we come up with thoughts here? What do I mean by extrema? Mins and maxes. Are there any mins and maxes here? No. Because this graph is just constantly increasing, so it's constantly going up, right? It doesn't have any spots where it goes up to a high point and then comes back down, or any spots where it goes down to a low point and goes back up. It goes infinitely down and infinitely up, but that does not mean, those are not extrema. So I'm just going to state on here, there's no extrema. Okay. What about zeros? Do we have any zeros? Zero. A zero at 0, yes, because remember 0 is where do we cross the x-axis, and we cross at 0, 0. So I'm going to write here that there is a 0 at x equals 0. And then the third piece we're being asked to talk about is the shape. You guys already told me from the beginning, this looks a lot like y equals x cubed, doesn't it? And if you graph on your calculator, so we already graphed y equals x cubed plus x. If you graph on a secondary one, y equals x to the third. It is very similar there, isn't it? Where are the differences? Right there at the origin, it's slightly different. What's the other monomial that's part of this function here? Besides x cubed, we have an x. What's y equals x look like as a graph? That's a line, right? It's that perfect diagonal line. Well, look and see if I graph y equals x on my calculator also. So I've got the x cubed plus x, the x cubed, and now the x. And I'm going to zoom in one notch. So I'm just going to go and do a zoom in and hit enter because you'll be able to see it better. So there's the graph of our question, x cubed plus x. There's x cubed, similar shape. And what do you notice about x right there at the origin? Does y equals x in my original graph overlap? That's what I'm trying to get you to see at least. Is that when you look at that original graph, and we can even take off if you want, we can even take off the middle graph and you'll see, so this is the x cubed plus x, and when you look at y equals x, what happens right there at the origin? They overlap briefly, don't they? Okay, so the idea here is, what I need you guys understanding is, the general shape of this graph is like x cubed, which is the dominant degree here. But then around the origin, our graph takes the shape of y equals x, is what's happening. And that's, so when it talks about how is it related to the monomials from which it's built, that's what we're talking about. Okay, so what I'm going to comment here is that the shape is much like y equals x cubed. So in general, shape is much like y equals x cubed. Near the origin, I'm going to say shape resembles y equals x. So being able to connect that the general shape of the graph is y equals x cubed, so shape is much like y equals x cubed, but near the origin, the shape specifically takes on the form of y equals x. Okay, let me know if you have questions on A. I'm going to get us set up to talk about B for when you're ready. Okay. You guys ready to talk about the graph here? We'll look at it in the calculator here in a moment. But if you just start plugging values in, what do you get when you plug in 0? 0, 0. Okay. What do you get when you plug in 1? 1 to the third minus 1 is going to give us 0. So 1, 0. What do you get when you plug in negative 1? Negative 1 to the third is negative 1 to the third is negative 1, and then minus negative 1. No. Negative 1 minus negative 1 becomes 0 again. Interesting look here. I'm not really set up to graph 2, but did you guys think about 2? 2 to the third is 8, minus 2 is 6. So 2, 6 is going to be up here, off how I have my graph set up, yes? Any thoughts about what this graph is doing? How do I have 3 points in a line, but yet my graph isn't supposed to be a line? Y equals x third minus x?
Is it doing the up and down thing?
Yep, the up and down thing. Okay. So y equals x to the third minus x. Does it still have that overall cubic shape if you're looking on the calculator? It does. But the idea here is it's going to go up through that first 0, down through the second one, and back up through the third 0. Graph isn't great there, but it gets the shape across, right? What does this mean this time about our extrema conversation? Do we have extrema this time? Yeah. So it said, graph the polynomial, locate its extrema. Do you know how to remember how to use the calculator to do that? You know how to do it. It was on chapter P test, chapter 1 test, both of them. I don't know. I can't keep track. So, remember second calc. I'm going to find the max first. Would it have helped? Did you guys zoom in on your calculators at all first?
Yes.
That might help, might it? I'm gonna get out of there. I'm gonna do a zoom. I'm just gonna zoom in. That way I can zoom in right around the origin. You could also, there we go. Zoom in. I'm gonna zoom in at the origin there, because does that give us a clear picture of what's going on there at the origin? And now, especially those of you with the older calculators, you can see the graph better, and you can see how to set up your line. So for a max, okay, remember left bound, I need to put my cursor to the left of that high point, hit enter. Right bound, I need to put my cursor to the right of the high point. So for me, that max is in between those. And then for a guess, officially, we just go back here. Okay, does your max match my max? You think there's a glare? There is a glare, there isn't there? Okay. So, there we go. Move it out of the glare up there. We have a max. I have 2 decimal places in my notes. So there's a max at negative 0.58 and positive 0.38. We also need to talk about the min. I will tell you this graph is symmetric. It would be symmetric about the origin here, if you want. So you could just change the signs on those. But if we do our minimum, okay, I want my cursor somewhere to the left of that low point. I want my right bound, I want it to the right of that low point. And yes, I officially just come back here and hit enter. Notice your minimum values are the same numbers, just different signs, yes? As I said, there is symmetry here. So we have a minimum at positive 0.58, comma, negative 0.38. Okay. What about zeros? Do we have any? Okay. We have a 0 at 0. Where else?
Negative 1 and 1.
Negative 1 and 1. Remember, zeros are wherever my graph is touching the x-axis, right? And you could find your zeros using the calculator. I feel pretty confident looking at the graph and what we've already done that where those zeros are. So we have zeros, and I'm going to say at x equals -1, 0, and 1. Okay? And the third piece is to talk about the shape based on the monomials that made this up. Well, overall, if we look at the shape of this graph, what's it look like overall? Does it still kind of look like y equals x cubed? Overall, general shape of the graph, it still has that general y equals x cubed look. And if I turn that graph back on, you'll kind of see that. Okay? What's your other thought here? Yeah. Last time it was y equals positive x, so we had that increasing line. This time it's y equals negative x. Well, doesn't our graph kind of go backwards there at the origin? So if I graph y equals negative x, and again, I think it'd be more helpful if I zoom in. So let me do a zoom in here. So here's the graph of question, x cubed minus x. And there's the basic x cubed. What do you notice right there about that negative x? It overlaps exactly at the origin, doesn't it? Okay. So again, our higher power, our higher degree gives us the overall shape for the graph, but that negative x determines more around the origin what's going on. So I'm going to say a similar statement like I made earlier. The shape is much like y equals x to the third near the origin. When I say near the origin, I'm talking about near 0, 0, right? Shape resembles y equals negative x. Okay, so I always kind of think it's neat to see how when you put various monomials together, how they create a graph. Maybe that's just me, but I always think it's kind of neat. It's a math nerd in me, sorry. Okay, questions on this section? So I'm going to go down and talk a little bit about what's at the bottom of the page. Okay. So at the bottom of your page, there are some typical shapes of cubic and quartic graphs. So first of all, cubic, when I talk cubic, I'm talking about the equation that is y equals x cubed, right? Okay. This first graph looks a lot like y equals x cubed, okay? This second graph, we just saw an example of, right? That's when you start putting some of these other terms in that you get the graph doing other things there. So those are examples of cubic graphs. Remember cubic, the power is odd. They're going to, what do I want to say here? We're going to talk about in behavior, and I'm kind of talking about it a little bit ahead of time. But remember odd exponents? They have in behavior is down and up or up and down, if you remember that from Algebra 2. So they always start one place and end the other place. As opposed to quartic. Quartic is a graph that is y equals x to the fourth. Those are all examples of what an x to the fourth graph could look like, depending on the other terms in there. We looked at this first one yesterday, didn't we? It's kind of like a flattened parabola. That's your basic x to the fourth without other terms with it. These other pieces that are your various w's, that depends on what pieces you had in. Is there an x to the second term in there? Is there an x term? Is there a constant? Well, the constant would just move it up or down. But, are there x to the third, x squared, and x terms in there? Those pieces are going to make these other options. So those are all examples of quartic-style graphs. Notice, a quartic has an even exponent. Even exponents, their end behavior is up and up, or if we had negative out front, it'd be down and down. So they always start and end the same. Okay? Now, some key information here. First of all, if, I just mentioned this actually, sometimes forget what it says in those upcoming sentences. If the leading coefficient is negative, the graphs will be flipped vertically. When we talk flipped vertically, that is the same idea as saying reflected, right? That is talking about reflected across the x-axis. Okay, so if that leading coefficient is negative, flip these graphs upside down. Kind of already talked about that. And we're going to spend a moment talking about this bottom piece. A polynomial function of degree n. Okay, so given your highest power, degree n, notice what it says. We'll have at most n minus 1 extrema and at most n zeros. Notice it says at most. Does it mean it's guaranteed to have those pieces? No, it's not guaranteed to have those pieces, is it? It just says at most. Now, let me show you an example. So, if we use, I'm going to use this middle W right here. Pretend that I just drew my x-axis through the middle of that W. Okay? Now, what degree is this? If this is a quartic graph, it is degree what? 4, yes? So the example we're going to use, and I'm going to write the information down here. The example we're going to talk about, there is a degree 4. So basically I'm saying that in this case, n is 4. Okay? I'm just trying to use this example to show what it means. It says, at most, n minus 1 extrema. Well, what would n minus 1 be in this case? 4 minus 1, which is 3. So, 3, at most, 3 extrema. And remind me, what do I mean by the phrase extrema? Mins and maxes, right? So there are at most, which means there could be 3. There could be less. What do you see on this graph I drew the x-axis through, this W here? How many extrema are there here? Are there 3? There are, aren't there? Because there's an example of a min, an example of a max, and another min. So that's an example of at most 3 extrema. Now, depending on where I drew, what if this x-axis had been up higher? Well, no, never mind. I'm on the next step here. Extrema would still be the same, wouldn't it? However, what if I'd use this first one over here? Would I still have 3 extrema? No, I just have 1 minimum on that first one. So it does just kind of depend on which graph we're looking at here. Now, it also says at most n zeros. So what's that saying? At most 4 zeros. So your degree tells you how many zeros there are. So in this case, there is at most 4 zeros. Do I have 4 zeros here? Where's the 0? Where my graph crosses the x-axis. 1, 2, 3, 4. So I end up with 4 zeros on this example. And this is where I was a step ahead of myself. What if I'd drawn that x-axis up higher? Would I have had 4 zeros? No, I might have only had 2 zeros. If I'd drawn my x-axis a lot lower, we might not have even touched the graph. I might have had no zeros. Okay, so this is just the at most scenario there. But it's good to understand that, okay, power of 4 could be up to 4 zeros, and thus could be up to 3 mins and maxes. Good rules to know, folks. Good rules to know. Okay, example 3. This one's going to be tough for me to talk about on here because it's more of a calculator one. I'm kind of looking on the calculator as we have been, but it asks us to superimpose the graphs of f of x, which is given there, and g of x, which is x to the third, in successfully larger viewing windows. A process called zooming out. Continue zooming out until the graphs look nearly identical. Take note of the window size and what are the similarities of the two graphs. So, if you will, graph these on your calculator. X to the third minus 4x squared minus 5x minus 3. And then in y2, I'm just going to do x to the third. I would start us with a zoom 6. We have our basic x to the third, yes? Looks something like that. Can you tell what the other graph is doing? It comes up, and then what's it look like it does?
Goes down.
Goes way down, which we can't even see because it's off the screen, and then it goes back up, doesn't it? And I don't know if that's a very great picture of it, but what did they ask us to do? They asked us to now try zooming out. And if we zoom out, so I'm just going to arrow down to number 3, hit enter, and I'm just going to hit enter again because I wanted to zoom out around the origin there. Now can we at least see the whole graph? Okay. Now you have kind of a better picture. They want us to do this until they look nearly identical. You can see why these are both x cubes, right? They both have that same general shape, except that one has other terms that cause it to really jump down. So I would say, yeah, zoom out again. So go number 3, hit enter an extra time. Okay. So what do we hit here? The problem with the calculators. It zoomed out quite a bit, didn't it?
You can barely even see it.
Exactly. It is hard to see. Do they look pretty identical? Are they getting pretty identical at this point? Yeah. And if I look at the window, it's because we're way out. Yeah. Notice we're at negative 160 by positive 160 is what my graph is zoomed out there. So it looks very similar there, doesn't it? I believe you can see a little bit of a difference on my calculator with the color graphics. I believe if you go out one more time, you can't tell any difference, if I recall. There's the blue one. There's the red one.
Oh, if you take it out one more time, it's like 2 straight lines.
Okay. And see, mine still have a little bit of a curve at this point. And at this point, yeah, we're at negative 640 by positive 640. So, in my opinion, I mean, we get to a point where we're too zoomed out. You can't even tell what's going on, can you? Because they're definitely not lines, but, you know, just the idea that these are the same shape eventually. Okay? They are looking very similar. So, let's see. So, a couple of things. I'm going to write a little bit about, you know, where we were similar and stuff. It did ask, what are the similarities of the two graphs? Well, we already talked about they're both cubics, right? They're both the y equals x cubed. And then we also want to mention that, what are these graphs both doing in shape? They're starting low and they are going up and increasing for the most part, right? Yeah, the one has to jog down for a little bit, but if you look at the graphs now that I have them pretty much identical, they're just both increasing. So these were some of the comments that I was going to write here. So I'm going to start off mentioning that they were very similar at the negative 160 by positive 160 window setting. So I just kind of wrote negative 160 at positive 160. They were the same, not even just very similar, but they're pretty much the same when we got to the next setting of negative 640 to positive 640. And I'm just writing those kind of as intervals, like, okay, that's where our window was at. In terms of similarities, we talked about the fact that they are both cubics. In other words, that form of y equals x cubed. And then I mentioned kind of at the end how both graphs are generally, they're increasing graphs, right? So that's the last thing I'm going to put. So both graphs are, I'm going to say generally increasing. And I guess I forgot to write that by the time you get to the end, I usually do a second picture here that shows that they're basically just, whoops, they look very much alike, don't they? Okay, running pretty much on top of each other. Okay, you guys have what you need from there? Trying to show you a page from the book. Show you guys these. There's a little bit of glare there, of course. And I think that's probably going to not make much of a difference. Okay, so what do I have? Just about 5 minutes. The next section there, we start talking about in behavior. And I already mentioned in behavior a little bit today. In Algebra 2, we used the words up and down. So in behavior, what is the graph doing as the graph goes off to the left? Is it going down to negative infinity or is it going up to positive infinity? And then what is the graph doing as it goes off to the right? Again, is it going up, which is to positive infinity, or is it going down to negative infinity? That's kind of what we're going to talk about here as we go into example 4, which will obviously be tomorrow. But notice what it says. When looking at a graph, we can describe a function's in behavior based on where it is going as x gets infinitely large or infinitely small. And so in this example, there is a chart in your book, and this is what I have up on the Elmo right now. But there's a chart on page 188. That is what I want to talk about right here. So I'm not going to really write anything in that space. We'll do some examples tomorrow. But for those of you sitting in the classroom here, the idea here, okay? If you look at like a traditional cubic, you guys see that well enough to know last year when we talked about end behavior here, we would have talked about the end behavior being down and up because it starts down and it ends up, right? So we talked about that last year. This year we get more into talking about the limits. And so the idea here is as the limit as x approaches negative infinity. So that's saying as x, as you're going left on your graph, as we're going left, where's our graph going? It's going down. And so down right here is expressed as negative infinity. Over here where it's going up, well, this is as x is approaching positive infinity. So as x is getting bigger and we move farther right, my graph is going up. Going up is expressed as positive infinity. Okay? This over here. As x approaches negative infinity. So as x is going left, where's my graph going? It's going up, and so this equals positive infinity. As x approaches positive infinity, so as we go to the right on the graph, where's my graph going? Going down, which we'll talk about being negative infinity. So the idea is using infinities instead of using the vocabulary up and down. Okay? That was our kind of beginner vocabulary in Algebra 2. In pre-cal, we transitioned to talking more about limits and using the infinities, which is what leads you to calculus here. So over here on this quartic, notice it's what we would call up and up, right? Up behavior. But in both cases, as x approaches negative infinity, so as we go left, and as we go right, what do both of these graph limits equal? They both equal positive infinity because they're both going up. Okay. Down here, notice it's down, down. What do both of my limits equal? Negative infinity. Okay. So we will pick up tomorrow, because that's a good stopping point right there, on example 4A. So 4A, when you come in, I'll try and remember have you guys get started on graphing 4A and starting to look at it. We're going to talk about extrema and end behavior. So when we talk about end behavior, we're going to talk about how to write these limits that I was just showing you. Okay? And we'll go from there. The homework on the board over there, I don't know if you compare what was up there yesterday to what's up there today. I added everything. That's the homework for everything. I just put it all up there because I'm not really sure where the cutoff point is anymore. So on page 193, you'll have 2 through 8 evens, 9 through 12 all, 18 through 28 evens, and 34 to 54 evens. So that 34 to 54 evens is the part that's added on, and that will cover probably the page that we'll get to tomorrow, if I recall. Okay? Yes. Hopefully, if we can finish the notes tomorrow, which I would like to, possibly, hopefully, maybe.
If not,
It'll be due Thursday. I'd like it to be due Thursday. We'll see what happens. Okay? And I think, yes, that's what I tentatively have planned, is it'll be due Thursday. So, okay?